Howdy folks, so for this video we're going to look at the enthalpy of reactions and how do we deal with that. Let's go ahead and get started, as this one hopefully will be a shorter one. Okay. Now, all reactions will by definition involve the absorption and release of heat energy. This is just true to nature, because the energy of our starting material and the energy of our product are rarely, if ever, the same. So this difference will be the heat that will either be lost or gained. Now, of course, these values can be directly determined by calorimetry and our calorimeters, as we have just seen. Every balanced reaction, from simple to complex, can be described by its own unique enthalpy of reaction value. You can calculate these, and these can be tabulated and can be shared around the world, that we can trustworthily report this, that if I burn hydrogen with oxygen under these conditions, it will produce negative 483.6 kilojoules per mole of hydrogen combusted. If I react and turn iron ore back to molten metal, under these conditions, it would produce negative 712.7 kilojoules per mole of running this reaction. This is per running the reaction as written one time. So the above reaction would have required 2 moles of hydrogen. The below reaction would require 2 moles of iron oxide to run it. This enthalpy is an extensive property, meaning the number of moles you use gives you a different amount of heat. More iron means more heat, which is good. It means you can burn more stuff to get more heat. So if I double the amount of hydrogen I burn, I get double the amount of energy. Because of the nature of a state function, if I were to reverse a reaction, the energy will have the opposite side. If I am going to split water into hydrogen and oxygen, it consumes 483.6 kilojoules per mole. This is one of the key problems with hydrogen fuel economy. I mean, yes, storing hydrogen is a problem, but the main source of easy hydrogen, other than stealing it from the sun, that's not really easy, but the main source is, we could split water. We have a lot of water on Earth. Unfortunately, the amount of energy we can get out of this is equal to the amount of energy we have to put into that. So unless there's a way to convert a natural source of energy, like solar power or wind power or something like that, into hydrogen fuel, we are at a loss to produce hydrogen enough to fuel our cars in a clean way. So hydrogen burning produces only water vapor. Yay! But if we have to burn oil or coal to get the hydrogen, it does not help us one iota. It just changes where we pollute. It still affects everyone equally. Now, enthalpy values typically have a subscript behind them presenting what they mean to represent. And delta H of Rxn means a reaction. Running a reaction is written. Delta H of SOLV stands for solvation, the act of dissolving something. How much energy is gained or lost when water has to break up the bonding. Vaporization, VAP, is to boil an object. Fusion is to freeze or melt something. the energy it takes to turn a solid to a liquid or vice versa. Now, because enthalpy is a state function, enthalpy only depends on the products and reactants of a balanced chemical reaction. Enthalpy does not depend on the reactions needed to get to the products. What happens if I burn oxygen with hydrogen and produce liquid water? Well, it would give me a different amount of energy. But if then I calculate the energy in there to produce from liquid water to steam, and I combine those two steps together, I would get the same amount of energy. Why? Because they end up at the same spot. The final products is 2 moles of water vapor gas, and the starting product is the same. When we burn coal, the main byproduct is CO2, but occasionally you can get incomplete combustion, which is carbon monoxide, which gives you less energy than if you're to completely go to CO2. However, if you're able to capture that CO, carbon monoxide, and redirect it back into the furnaces, you can keep on burning it to form CO2. And you do not lose any energy if you're doing that. The energy lost is only if you're letting that CO escape. If you're recapturing and reburning it, you get the same amount of energy as if you completely burn it. So being able to completely burn the things makes sure you don't waste anything. So it doesn't matter if you break it down into 2 steps, as long as the starting material is carbon and 1 whole oxygen, and if you add all the reactions together, that's what you get. And the final product is 1 CO2, and that's what you get. That's what it means to be a state function. Now, Hess's law is a beast, but Hess's law is the direct application of the state functionality. If each reaction has its own specific enthalpy, it is possible to combine relative reactions together to understand a complex situation. Hess's law simply states that when you combine 2 chemical reactions together, the enthalpy of the new chemical reaction becomes the sum of the enthalpies of the combined chemical reactions. Meaning, if I double a reaction, I would double its enthalpy. If I add 2 reactions together, I add their enthalpies. If I reverse a chemical reaction, I reverse its enthalpy. Here's just some direct, easy comparisons. Burning 1 mole of methane produces 802 kilojoules of heat. Burning double the amount of methane gives you double the amount of heat, 1604 kilojoules. If burning hydrogen gives you 483 kilojoules of heat, well then splitting hydrogen requires 483 kilojoules of heat. That's how it works. But so this right here is the most difficult looking problem we will see. That glucose. If I want to study the formation of glucose, how does glucose, a simple 6-membered sugar ring, the simplest sugar we have, how could that be formed out of its elements? Well, that will never, ever, ever directly just form out of its elements. It needs some sort of guidance. If I just mix carbon and hydrogen and oxygen together, we will never just, boom, magically get glucose. There has to be some intelligent design that's going in to put it into place. So in order to understand this and understand how much energy would be involved in this process, we have to go about in a roundabout way. So instead of studying this equation that we want, we're going to study these three equations which we know perfectly. That we know if we burn carbon with oxygen to complete combustion, this is the energy involved. If we burn hydrogen to completion, this is the amount of energy involved. And if we burn some pre-existing glucose to completion, this is the energy involved. So if there's a way to add these three equations together to get the above equation, then the relative delta H's will be related. So looking at this, carbon only exists in equation 1, pure carbon. So I need 6 carbons to be reacted. So I need to multiply reaction 1 by 6. Because I multiply reaction 1 by 6, I multiply its enthalpy by 6. The amount of hydrogens I need in the above equation is 6. Hydrogen only appears in equation 2. So I need to multiply equation 2 by 6. And so I multiply its enthalpy by 6 to get negative 1714.8. And glucose combustion, while glucose is, this equation 3 is the only source of glucose, it is on the wrong side of the equation. Glucose is a product in the above reaction. Glucose is a reactant in the combustion. So with that in mind, we need to reverse the bottommost equation. And so by reversing it, I get 6 water and 6 CO2 forms glucose and 6 oxygens. And we reverse the sign, so it, instead of being exothermic, it's now endothermic. And when we add all the reactions together, 6 carbons carries down, 6 hydrogens carries down, 6 CO2s will cancel with 6 CO2s. 6 of these oxygens will cancel with 6 of those oxygens. But 3 of these oxygens are left behind and are going to stay down here. 6 waters will have to cancel with 6 waters, and so we're left with only glucose as the byproduct. And we'll notice that now matches the above equation. Well, now I need to add these numbers up. When I add these numbers up, we get it would produce 1,271 kilojoules worth of heat. That's what this reaction would entail. Now this is a direct and more relevant and easier to do version of this. That NH3, which is aqueous ammonia, and nitric acid and aqueous acid react to form ammonium nitrate, a solid. That's not very likely. It will react, but the likelihood of it solidifying and kicking out all the water is nada. So what would be the energy associated with this? Negative 120. I'm writing our numbers down. And ammonium nitrate solid breaks down into NH4 plus and NO3 minus. Delta H of positive 25.7. Okay. For the last slide here. Okay, well, look at this. And really, all you have to do is go, well, we got this and this right here. So that one's good. But we got this here and this here. So I have to reverse this equation. NH4 plus and NO3 minus goes to NH4NO3. And that'd be a delta H of now negative 25.7. Now when I add this and this, each of these terms cancel out, and we are left with HNO3 and ammonia give you ammonium nitrate. So the delta H would be just simply the sum of this and this, so negative 145.7. Even though this produces a lot of energy, it doesn't happen because there's other factors involved, such as solubility and entropy and all sorts of things that are going to keep this from just magically crystallizing. That's where we're going to stop here.